Olá a todos and welcome to another mathematical modeling video. This video we are continuing the selling your art on the beach video from last time. I will put the link up here. In the last video, Javier was a student that dropped out and decided to sell his art on the beach. So we saw an optimization model to decide how much of each product Javier should build: a bracelet, a necklace, and an earring. And we saw that the best solution was to sell a lot of bracelets. Following that strategy, Javier noticed that selling a lot of bracelets was not working because the demand for bracelets was not high enough. Furthermore, people were asking about the other products and he usually did not have enough to supply those products. So there was a simple mistake. Javier was not building to supply the demand. He was essentially building without considering the demand at all. So in this video, we're going to look at two ways to consider the demand on your mathematical model. And I'm going to let you judge which way is better. And if you think of another way, please leave a comment saying what do you think we should use. And we might consider doing a video about that. So we're going to take into consideration the demand for the products, or that essentially means how much of the products are going to be bought at a given price. And we're going to look at two strategies. So the first strategy is that if we have more products than the demand, those extra products are going to be bought at a discount. So the assumptions for this strategy are that we know the demand for the initial price. For instance, we know that at 25 euro we can sell 4 bracelets, but we are also going to add the assumption that if I then decrease the price of our product to this column right here, I can sell all of the other products. So that's a way of, that's essentially a sale that I can have. So for now, not much more changes. So the cost of the materials is the same, and the other values are all the same. The modeling has one big part. How do we deal with this price changing depending on the amount that's being sold? So let's look at an example at a smaller scale. Look only at the bracelets, okay? So we can sell 4 units at 25 euros and 8 euros we can sell everything else. This is the revenue for that bracelet. So up to 4 bracelets, my revenue is 25 times Q. And after that, I have sold 4, so 25 times 4, plus however many above 4 times 8. So essentially I have 2 slopes on my objective function, my revenue function. It is a concave function and we are maximizing the revenue. So that's important. We are maximizing and the revenue is concave. So don't worry too much about that if you're not into the math of this, but this is important. This function is not linear. It's essentially linear in sections or piecewise linear. Because it is piecewise linear, we can deal with that. And there is a simple trick to handling that, which is to split the quantity into 2 parts. The first part of the quantity will be the quantity under demand. I'm going to be using Q underscore here for this example. And the quantity over demand, which is Q over score. So we can, instead of writing that, we can write that the revenue is 25 underscore Q or underline Q plus 8 overline Q. Right? So go back here. This is 25 times Q, which is the initial Q. And everything beyond that is going to be this Q minus 4, which is going to be our overline Q. Okay? So essentially we have Q underline less than 4 and Q overline is greater than 0. That's it. I'm going to change everywhere that Q appears to Q underline plus Q overline, and that's gonna allow the rest of our model to be the same as it was before. So for instance, the time to build a bracelet is gonna be 2.5 hours. So I'm gonna say 2.5 times Q underline plus Q overline. So that's essentially the change that I have to make in the model. Instead of using Q, I use the sum of both of them. So why does this work? Let's look at this other image right here. So if you have 0 production, right, for some reason you don't have enough time to build any bracelet, have 0 production, So that's easy. Your normal production, which is the Q underline, is 0, and your extra production, which is Q overline, is 0 as well. But as soon as you have any kind of production, you have a choice to make. So you only have time to build one bracelet, for instance. So you can either build 1 normal and 0 extra, or 0 normal and 1 extra. So how does our model decide that? This is where the maximization part comes into effect. If I sell 1 normal and 0 extra, so this point right here, I am closer to 25. And if I do the opposite, I am closer to 0. So it is financially better. It gives me more revenue if I sell 1 normal production and 0 extra production than the opposite. Okay, so that's essentially by maximizing the problem, I naturally choose the normal production instead of the extra. So that happens for other values as well. For instance, 3. If I have to choose between 3 normal production and 0 extra, or 2, 1, or 1, 2, or 0, 3, the one that's gonna give me the most revenue is by building 3 normal productions and then nothing of the extra production. What happens when I go over 4? So at 4, this is still the case. At 5, I am constrained to build only 4 normal productions. So that's why it's important that you remember to constrain here, Q underline up to the demand, which is 4. And now I have to choose whether I want to build 4 and 0, 4 and 1, or 3 and 2, and 2 and 3, etc. And again, the best one is this here, maybe around close to 100 probably. So around here, I'm gonna choose to build 4 normal productions and 1 extra production. So I'm essentially saying always maximize the normal production first, and then you build the extra production. And this is gonna keep happening over and over and over. Anytime that I go down in this path is gonna be worse, because I could be making more money by going up. And anytime that I go up in this slope is gonna be worse, because I could be making more money by just having more normal production. There are many other points that I could choose here, by the way. Anything that's inside this polygon, any integer combination, if I'm gonna build up to 7, then it's best that I maximize it, okay? So first thing to notice here is that this value here, this corner, has an objective value, has a revenue, and this value is this one, okay? So that's essentially what changed. Instead of having a single variable and a single revenue, I now have 2 variables, and at first I have a revenue that depends on these 2 values. But when you actually try to maximize, you're essentially forcing your choice to be extra production equals to 0. And then when your normal production is 4, you increase the extra production and keep your normal production at 4. So you can use this notebook to explore rotating this. Maybe better to understand, maybe not. But I'll leave it for you to decide. And the second important thing to comment here is that I am only looking at the necklaces, and I'm just, for some reason, constraining the production to be equal to 2. So I'm not looking at any other constraints, I'm not looking at any other variables, I'm not looking at anything else, just that for some reason the production is 5. How do I choose 5 production between all of these values? So when we actually model these, there's going to be more interaction between the products and how much I can build of them. So it's not as trivial as it seems, and that's why we model things with optimization. Okay, so let's talk about the model. The model has not changed a lot. We have 2 new things. The first one is the discounted price of P. We had the price, now we also have the discounted selling price. And we also have the demand for the product P. This is the demand of product P at price, selling price P. The variables have been split into 2, so the prod normal is the production at full price, and the prod extra is the production at a discount. So now we have 2 decision variables. These are 2 vectors of decision variables. instead of a single one. It's important to notice that prod is not a variable anymore, and we are going to be creating an expression, and that says that prod is going to be prod normal plus prod extra. Okay, if you see prod in the code, that's actually prod normal plus prod extra. And that's a great thing about expressions. If your modeling language accepts expressions, you can just say, hey, I'm going to change the name prod to be this thing, and the rest of the code is going to be essentially the same. So the revenue changed because the selling price is important for the revenue. So selling price times the normal production plus the discounted selling price times whatever else I sell. But the rest here, the total used materials, don't depend on the selling price, the material cost, and the time expenditures. So they, the material cost doesn't use any product, but the time expenditure and the used materials, they use prod, the expression now. Same thing for the objective. We still want to maximize the revenue minus the material cost. The new constraints that we have are still kind of easy, though. So the production under demand, which is prod normal, must be limited by the demand of P. So again, this is a single variable being limited. It's a very easy to write constraint. No negativity. So being more explicit, we can always say no negativity for many of these variables. These exist, of course, to make sense of the production. So the production cannot be negative, but also prod extra must be positive because of that combination that we had. Otherwise, we could build negative amounts of prod extra, so we could build more of prod normal, which would break our model. That's not what you want. Of course, we still have integer production, and the time availability is still the same. So now let's get into the jump model. So remember, if this is not your kind of thing, you can just skip ahead in the chapters. Not a lot has changed here, but I have made one modification because, as I mentioned before, this is a much easier way of handling things. Instead of using the whole products vector, I am now using the indexes, which makes things much easier. So now you can see P equals 1 to non-products instead of P equals products. So the prod normal is a new variable. It is limited by 0 below and by the demand P above. So notice the demand is already here because it's a constraint on the variable. And one way of constraining the variable given the demand is by having P equals, and then you just put the variable here in the demand vector. The prod extra is P equals 1 to known products. Again, not a lot going on here. The prod is prod normal plus prod extra, so these are vectors, I can just sum them, and because I'm doing this, a lot of the rest of the things going on here are gonna be the same as the last code. The total used materials, for instance, I have changed here to be M equals 1 to known materials, and the sum is going for P equals 1 to known products, but I'm just multiplying by prod, nothing else has changed. Total material cost has not changed. The revenue has changed because of the selling price, as we mentioned. The normal production is being used here instead of the previous production. And the extra production is being added here with a discounted selling price. The profit is the same, the time expenditure is the same. We're still maximizing the profit. We are still constraining our time expenditure, and then we optimize the module. I'm returning a lot of extra things. This can be useful. Instead of returning everything, you just wrap on a function and return a few things, because I don't want to clutter my environment, my Pluto environment, and then because I can also say exactly what I'm returning in a dictionary. That's it, let's go back. So now looking at the results, here we have the time availability, 0 hours at start. If I increase this to 1, nothing changed because the minimum production, I think it took 2 hours or 1.5 hours. If I use 2 hours, I'm gonna have a single earring, and you can see here that the normal production was used, not the extra, because the model is right. If you have 3 hours, it's best to build one bracelet instead. It gives you more money. If you have 4 hours, you can build a bracelet and an earring. 5 hours, 2 bracelets. So as you remember from last time, the bracelet was the best profit margin. So if you could build only bracelets, that would be better. And here is essentially what's happening. So 2 bracelets. If I have more time, bracelet and a ring, earring. If I have more time, 3 bracelets, and that repeats until I reach 4, which is the maximum of the number of bracelets that I can build under demand. Okay, so now things will begin to get interesting. If the bracelet still has the best ratio, I could just build more bracelets, and then I would have essentially a bracelet shop. But the price of the bracelet decreases a lot after 4 units, right? So it could be that it's not so much more profitable now to build bracelets, and that's gonna probably be the case because the necklace and the earrings are selling by a lot more than a bracelet actually. So if I have more time, 12 hours, it is now best to build an earring. If I have 13 hours, build 2 earrings. 14 hours, build a necklace. So the necklace is more valuable than 2 earrings. And well, 3 earrings is better. And then if you continue to increase, you can see that you have some dynamics going on here. So 4, 2, and 3 are our demand. At this point, we have satisfied all of the demand that we had at this price. If I don't decrease the price of any of my products, I don't sell anything else. Well, not me, Javier. I'm not selling anything of this. Javier is. So let's say that I decrease the price. Now I can start selling more things. For instance, I'm selling an earring, or a bracelet, or 2 earrings, or 1 necklace, and so forth. So looking at this, I can see that what's most valuable for me to build are extra necklaces. So if I want to satisfy the demand, it's profitable to satisfy all of the demand of all of the products. And whatever extra time that I have, I just build more necklaces. And that's it. If I still have time that can't be used to build a necklace, build more earrings. And that's how we satisfy the demand for our week using 40 hours. So this is the profit over time. Again, you can see kind of clearly what's happening. We still have in some cases no increase in the profit because we don't have enough time to build anything else. Now, so we have these steep increases. So essentially here I think we build 2 bracelets, then we build another 2 bracelets. Maybe here we build the next bracelet, I don't remember. But in some point here, the maximum amount of bracelet was reached. So we started building more things like the necklace. Then we reached the maximum of that, and then we reached the maximum of earrings. And now around here is where we are only building extra products at a discount. So our profit margin decreased a lot. Okay. So this can be actually a good point to decide, hey, I'm only gonna work 22 hours and not gonna work the rest of the time because it's not profitable. Maybe that's a good solution for Javier. So now let's look at our second strategy. The second strategy for dealing with the demand is to assume that demand is a function of the price, which it is. But we're gonna use that explicitly in the model. And that's exciting, because that's going to make our problem much harder. Although it doesn't look like it from the start, but it's going to be much harder to solve it. Our assumption now is that we know how the demand behaves in function of the price. We're going to use a simple assumption that the demand has a linear dependence to the price. So it is an intercept value plus the slope times the price. And we are going to assume that we know the intercept and the slope values. these are the values in graphical form for the bracelet and for the necklace and for the earring. So you can see here what happens if the demand is a function of the price. When we decide the price here, we are essentially saying how many of our products we're going to be selling if we build all of that, okay? So if I set the price of the bracelet at 25 euro, I'm going to be selling 4 bracelets. If I change the price to 18 euro, I'm going to be selling 7.5 bracelets. Of course, could be integer, but that's an added issue. Let's not think about that. If I change the price to 7, I'm gonna sell about 13 bracelets. The question is how much I make from these bracelets, and how much I make is the quantity that I'm selling times the price. So this blue rectangle here, the area is the revenue, okay? Quantity times price. So that's exactly the revenue. So I'm essentially looking to maximizing this rectangle, the area of this rectangle. I like this example a lot because it's very simple when you do it in single variable calculus as an example of maximization. But anyway, let's look at the right side here, which is the revenue, which is exactly the area of this rectangle. You can see here there is a clear maximum, or in the top of this parabola, around 16 and something, 16.5 maybe. We're going to be selling around 8 or 9 products, okay? So if I only look at the demand and the price, and I ignore all of the constraints, I'm saying, hey, Javier. Or Javier is saying to himself, I don't know, I'm not Javier. So he says, hey, I'm gonna sell my bracelets at 16 and something. And because of that, I know that I'm gonna be selling 8 of them. And because of that, I know that I'm gonna be making about 130 euros, okay? Of course, that's ignoring a lot of things. That's ignoring that I actually have demands for necklaces and earrings as well, and that I don't have enough time to build all of those things up to the maximum of their demand, okay? So if you knew that you had enough time and you're just looking to maximize the profit of these things and not build any more of them, you can just look individually at each one of them and maximize the revenue by computing the derivative of this function, for instance. Okay, so that's a simple solution. However, that's not what we are doing. What we are doing is looking at maximizing, given the interaction between all of those things. So now let's look into the model. You can also see the values, explicit values that we use above, but we can ignore that. We only care about the model. So there are a few things going on in this model. The first one are that we don't have the demand that we had before. We instead have the intercept and the slope, because we're going to be using these values explicitly in our model. But also we don't have the selling price anymore in the parameters, because the selling price has to be decided to then decide the demand and to decide how much production I'm gonna have. So here instead we have a new variable, which is the price of the product P in euros. So the decided price is our new variable. I changed the name to be more explicit. That is not the selling price. We also have the production, and the production is going to be limited by the demand, as we had above. We cannot produce more than the demand, because we're going to assume that everything that we produce is going to be sold. So we have to produce up to the demand. So we could in principle say that the production and the demand are the same thing. We're not going to do that for reasons that I'm going to talk about later. But most importantly, the decided price is a variable now along with the production, and that's going to change things a lot. So first we have a new expression, which is going to be the demand. So the demand given a price, I'm being explicit here to differentiate between our other demand. So the demand given price is the demand intercept plus the demand slope times the decided price. So demand given price is an expression that depends on the variable decided price. And the revenue changed a little bit to be decided price times production. So it's not selling price anymore, it's decided price. And here, this revenue has a variable times a variable. This is nonlinear, and this changes things a little bit. So when you have only integer variables, having a nonlinear function makes your problem sufficiently harder. So our initial solver, the solver that we used before, does not handle quadratic objective functions. There are other solvers that handle that, and depending on whether you're buying or not a solver, you don't have to worry about that at all. But for us, we are only using open source solvers. We're going to be changing the solver. But we can talk more about that in the implementation. The total used material and the total material cost and the time expenditure, they don't change at all. They are just the product, just prod P here, so nothing has changed. The objective is maximizing revenue minus the material cost. That has changed a lot, but internally because of the revenue changes. And now we have some constraints. New one, which is the product. The production has to be limited by the demand given price. This is now a constraint and not anymore a bound on the variable. So in our previous example, we had a bound on variable prod, but the demand given price now is actually an expression. So it changes according to a variable, and because of that, this has to be actually explicit as a constraint if you are differentiating between upper bounds and normal constraints, okay? If you don't look at the implementation, you won't care a lot about this, but anyway. One important thing here is that since we are maximizing, we are, in theory, always having an equality. The production will always be equal to the demand. Why is that? So if so let's say the maximization of the production is 4 and the demand is 5. Now the demand is actually given the price. So if I'm only building 4, so that's the only thing that I can build for some reason, I can increase the price, so I can decrease the demand, so the demand is 4. And so I'm making more out of these 4 products. And on the other hand, if I have a demand of 5 and I am building 4, but I have time to build more, I can build one more unit and make more money out of it. So there is no reason for the production to be strictly less than the demand under what we have here, under these conditions that we selected, okay? So in theory, the production is equal to the demand. Why are we not using that explicitly then? Because numerically, the solver might have issues solving that. So because the production is integer and the demand given price is a floating point, it might be that it's harder for the solver to make this an equality. For many solvers that won't matter, and I actually have not tried it for this solver that I'm using, but I thought it would be better to just leave it like that. So another reason to use an inequality instead of an equality is because maybe in future improvements to this model, the demand itself has to be limited by some other things. And because of that, the inequality may actually happen. So to be future-proof, let's leave it as an inequality. Even if this does not improve the life of our solver, it should not make our solver work harder, I think at least. So the rest of the variables are still pretty much the same. The time availability has not changed. The non-negativity of the price as well. And the integer production, we don't have an integer price. The price is floating point. So let's talk about implementation now. The first thing that we are going to talk about is that we are using a new solver. We are using solver Skip. Again, an open source solver. Skip was actually made open source some time ago, maybe a few months, maybe a year. And that's good. Before that, I had used Gurobi, but Gurobi is a paid solver, so you would need either an academic license or you have to buy it. And Skip, as far as I know, it's completely open source. It has Apache 2 license, so you can use commercially. We have to change that because CBC does not handle, and most solvers actually don't handle quadratic objectives with integer variables. If you only have nonlinear variables, that's easy. But if you have integer variables as well, then it becomes a hard problem. Luckily, we can just change here and that's it. I also have attributes for skip. Importantly, I have the gap being 001, although as far as I'm aware, it looks like the gap was always 0. If you don't know what the gap is, don't worry about it. The model itself is quite simple. We have two variables, the product and the decided price. The production and the decided price. The demand given price is an expression, which is the demand intercept, plus the demand slope times the decided price. This is a dot product, so element wise. So for each product, which is each element of these vectors, I'm multiplying them and I'm adding to the intercept. The total used material has not changed, the total material cost has not changed, and the revenue has changed to be the production times the decided price, not the selling price anymore. The profit is revenue minus the total material cost. And the time expenditure, which I just edited, is the sum of hours assembled times the production, which is the same as before again. Maximize the profit. Extra constraint, the expenditure must be less than the time available. And you have a new constraint, which is the production is limited by the demand. Okay, you can see I do things on the fly. So again, I'm returning a lot of things that I'm gonna be using in my plots and the results, but that's the model itself. Not a lot has changed. That's impressive. If you think about it, the real changes are the new variables and the revenue changed because of that. And we had to change the model, but pretty much it's all the same. Now let's look at the results. So I have added a column here for the demand. Just so we can see that it actually is the same as the production. Of course, for the case where the production is 0, so what is the price for this? I cannot build anything, I don't have availability. Well, I don't have anything in the price that's gonna make a difference. So probably the price is set at 0, and because of that, the demand is very, very large. That's not a real case. That only happens because I really don't have time to build any product, so it doesn't change at all my revenue or my profit. So as soon as I have time to build anything, so when I build, I have time to build one earring. I set the price of my earring to 11 euro, and I'm going to be selling one earring. If I have time to build one bracelet, I'm gonna set the price of the bracelet to 31 euro, and I'm gonna sell one of them. If I have time to build more, I can sell one bracelet and one earring, or two bracelets at 29, or two bracelets and one earring at 11, and so on. And you can see that's always the case. As the more you build, the more cheaper you can sell them individually, but you make more profit. Otherwise, you will not be doing that choice, and that happens continuously. And interesting, you can see here that for the bracelets, we have 4 bracelets, which was our previous demand, and 1 necklace. And we were essentially always increasing the bracelet. So we have 2 bracelets, and now instead of having 3 bracelets and 0 earrings, we have 2 bracelets and 2 earrings, and that happened again for 3 bracelets and 3 earrings, and then 4 bracelets and 4 earrings. So it is a much more complex and nuanced selection, which is super interesting to me, at least. And you can see in our extreme case of 40 hours is a little bit more balanced. So 21 euros for the bracelet, and we're gonna sell 6 of them. We sell necklaces for 40 euros each. We're gonna sell 4 of them, and the earrings at 8.5 euros, and we're gonna sell 6 of them. And this is our profit curve. Much more nuanced, much more interesting to see, and it kind of looks quadratic a little bit. If you smooth a little bit, it looks much more quadratic. You can see that it's kind of stabilizing a little bit, it's decreasing, you have some diminishing returns. So every increase in price, or let's say you can work 2 hours more and 2.5 hours more and build another bracelet. But if you build another bracelet, you're gonna make less per bracelet. So eventually you're gonna get to that situation in the top of our parabola where it doesn't make sense to increase the price and sell more because you're gonna be making less in total, right? So this is kind of reflected here. You have some diminishing returns in this slope decreasing. We only had 40 hours, so we still have time to make more. So if we had more hours, or if we could build them a little bit faster, we could still make more profit. But what happens if I actually have a lot more hours? So I'm gonna make a little edit here. I'm gonna change to 80 hours. And if I change to 80 hours, I eventually get to a point where it doesn't make sense to build any more products. So around 50 something hours, essentially Javier could just say it's not worth it anymore. Stop working, 50 hours is enough. I'm not gonna make any more money from this. So I'm gonna leave this as a question to you. So let's say that Javier found a partner and together they have 80 hours, but they notice that it doesn't make sense to spend 80 hours always building more. If they build more and they decrease the price to satisfy the demand, to actually sell everything that they build, they're gonna make less money. So what they are doing is they are building a lot more and they are not selling the extra products. The extra products are getting stuck, so they are having inventory. What do you suggest them to do? What would you do in this situation? So I hope you have enjoyed this exploration of the selling your art on the beach problem. Javier got to the point where he can actually use the demand to better decide the price. We have not explored how much more money or less money he's making in comparison to the previous case, because these values are essentially random. I'm just selecting them to look nice. They don't make any real sense. But the most important part are the models themselves. I left you with a question. So what would you do if you're in a situation of strategy 2 where you don't actually have an advantage of if you build more products and decrease the price? What would you do in that situation? I am also going to leave you with another question regarding strategy 1. So we noticed that strategy 1 was I'm going to sell things at a given price, and then I'm going to decrease the price so I sell all of the other things. So instead of doing that, what if you did more steps between the last step? So let's say that you sell the bracelet at 40 euros, but you can only sell 2 if you do that. Then if you decrease the price to 30 euros, you can sell another 2. And if they decrease the price to 15 euros, you can sell another 3. And then if you decrease the price to 8 euros, you can sell all of the other bracelets. How would you model that situation? Okay, leave that in the comment. How would you model that situation? So that's it. Thanks a lot for watching. I hope you enjoyed it, and if you did, please like and subscribe. If you did not enjoy it, please leave a comment saying why you did not enjoy it, so that we can improve it for the next video. Thanks a lot, and I'll see you next time. Bye bye.